still on standby. Good day, and welcome to our webcast on machine learning and pattern recognition use in predictive maintenance and quality, brought to you by CFE Media and Technology and sponsored by Avnet, Epicor, and Oracle NetSuite. I'm Kevin Parker, an editor with CFE Media and Plant Engineering Magazine. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to RECEP at recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. To take the Learning Unit exam, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a separate browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. You see before you a list of the learning objectives for today's session. Here are some tips to help you get the most from today's webcast. If you experience issues with the slides or audio, refresh your browser or click the Refresh Media button under the presenter's picture. Control the volume of this webcast by adjusting the volume on your computer or on the webcast platform. If you are having technical problems with audio or the slide presentation, click on the question mark at the right-hand corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. The Ask a Question box is also used to ask questions of our speakers. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded. You will receive an email in a week with a link to the on-demand event. To download a certificate of completion, a PDF copy of the presentation, and other additional resources, use the Event Resources tab on the left-hand side of the screen. Those documents will also be available with the on-demand version of this webcast. The exam will be posted on CFE Media websites with the on-demand version of this webcast. The exam is for one RECEP ASEC Certified Professional Development Hour. Before beginning the presentation, we invite you to view the following short videos provided by today's sponsors, Avnet, Epicor, and Oracle Suite. At the conclusion of the video, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned.
The Internet of Things. It's benefiting businesses and industries across the globe, and it's moving at a fast pace with so much complexity that it can overwhelm even the best development teams. Introducing IoT Connect Platform from Avnet, a secure, cloud-based enterprise IoT and AI platform that simplifies the complex. This Microsoft Azure-certified, developer-friendly middleware platform brings together IoT hardware, software, applications, data analytics, and artificial intelligence capabilities. It comes equipped with a feature-rich toolkit that is easy to use and significantly reduces complexity, cost, and time to market. At Avnet, we help your business succeed by putting innovative technology to work. With our IoT Connect platform as part of your strategy, all of your stakeholders can collaborate and leverage our platform to speed up the design, development, deployment, and operation of IoT solutions.
If you don't know your numbers, you don't know your business. I learned this the hard way with my first company, so I created NetSuite, the world's #1 cloud business system. NetSuite gives you the visibility and control you need to make smart decisions and grow with confidence. That's why companies who use NetSuite grow 3 times faster than the S&P 500.
Schedule your free product tour right now at netsuite.com/grow.
Manufacturers are facing a barrage of information about how new disruptive technologies will change the face of their industry. But for manufacturers to embrace mobile, social, analytics, cloud, and Industry 4.0, they must have a clear understanding of the technology value add within the context of today's business environment. With all this talk about Industry 4.0 and data deluge from all the interconnected devices on the factory floor and analysis in the back office, manufacturers may wonder, where does ERP fit into this new digital frontier? The reality is that ERP is more relevant in this equation than ever before, and manufacturers need the ability to contextualize data and integrate it into downstream process flows. To do this, ERP systems must be reimagined to meet the needs of new and emerging manufacturing technologies. Responsiveness demands simplicity and mobility, with tools designed to meet the specific needs of specific users. With an ERP system that delivers this, manufacturers can check off a big box on their Industry 4.0 readiness checklist and make good on the promise of real-time, actionable intelligence.
Welcome back. I'd now like to introduce today's speakers. Dr. David Siegel is the Chief Technology Officer for Predictive Maintenance Corporation. His current role includes developing the company's technology roadmap, as well as leading the implementation team for predictive monitoring and machine learning-based solutions. Prior to joining Predictive Maintenance, Dr. Siegel was a research assistant at the Center for Intelligent Maintenance Systems at the University of Cincinnati. Siegel has written or co-written over 40 papers in the area of condition-based monitoring, intelligent maintenance, and machine learning solutions for improved diagnostics and prognostics. Mo Abu Ali is managing partner and chief evangelist with IoT LLC, located in the Cincinnati area. IoT helps clients create a competitive advantage through digital transformation. In addition, Mo is adjunct professor at the University of Cincinnati College of Engineering and Applied Science. Mo has a doctorate in the philosophy of industrial engineering from the University of Cincinnati. Thank you for joining us today, Mo. The floor is yours.
Kevin, thank you very much for the introduction, and thanks to CFE Media for hosting our presentation today. Very pleased to be here again, actually, with Dr. David Siegel. A few months back, we provided a presentation with CFE on predictive maintenance for zero downtime manufacturing. And today is actually the perfect second piece of that, which is predictive quality using AI and machine learning for zero defect manufacturing. So a pleasure to be here. Very briefly, IoT Co. and Predictronics, we focus on bringing industrial AI applications to manufacturing. We work heavily in discrete manufacturing, including automotive, and we provide a turnkey solution around analytics, in addition to the needed education, training, and connectivity to the plant floor, as well as other manufacturing IoT solutions that may be required by the customers. So our agenda for today is I will set the stage of why folks out there are using AI for predictive maintenance and predictive quality applications, which are key technologies that fall under the fourth industrial revolution domain of experience. Dr. Siegel will go through the technology and relevant use cases of using AI for predictive quality, and I'll give a conclusion around how you can get started and how you can gain ROI by using AI and these types of solutions. So let's get started. We are believers that it's always very important to start with the business case. So the application of industrial AI and machine learning in manufacturing requires proper justification to ensure that those solutions are affordable, ROI-based, scalable, and can lead to value generated to the manufacturer. And one of the key metrics used in manufacturing today to measure performance of plants is the OEE metric, overall equipment effectiveness, which is your availability, that's the uptime of your assets, the performance and efficiency or the speed of running your operations, and quality. And in our conversation today, we'll be really focusing more on the impact to the quality metric of the OEE measurement. Of course, by using analytics, there is an improvement to labor productivity. And by using analytics, there is also improvement to the overall health and maintenance of assets on the factory floor. There is a transition and a transformation from a reactive and a time-based mode of doing maintenance on assets to a condition-based and a predictive and preventive approach to doing maintenance on assets. So in many cases, actually, and you'll see this in some of the case studies, you can use the same data for predictive maintenance purposes and predictive quality purposes, but it surely is dependent on the application and dependent on the business case that you're looking to achieve. We will focus our conversation today on the technology, templates, and case studies that are relevant to a zero-defect manufacturing operation. And the idea here is detecting, reducing waste and scrap on the manufacturing floor, which can actually be very hard ROI for any manufacturing business. Very briefly, two quick case studies. The first one was focused on predictive maintenance, and we've actually shown that case study a few weeks back when we did the first part of this webinar. This is focusing on assisting clients to use machine data and to focus on the asset itself and focus on improving and sustaining high levels of uptime and availability on the asset. Whereas in the case of predictive quality, we're actually correlating and mapping machine data or process data to the actual quality of the part or the product that is being produced. And Dr. Siegel will show this example at the end of the case studies, but in this example, we're actually working on high-pressure die casting cells, and the industrial AI is trained to make predictions of whether you're making a good part or you're going to make a scrap part within very fast responsiveness time, because you're making parts within 15-second cycle, for example, in this case, and the AI has to make prescriptive decisions. We're actually prescribing to the high-pressure casting machine and informing the machine, will you be making a good part or will you be making a defective part? So that the robot on the casting cell would actually pick it up and auto-segregate it to a good bin or a reject bin automatically without any human involvement. So predictive quality is mission critical. It has to be responsiveness within less than cycle time of the machine or the part. You need to make decisions. And it can be prescriptive. If the machine allows, we can actually feed data back to the machine and make decisions and support the machine to actually take action without human involvement. So when you're building your strategy for industrial AI and the application to your business, always think of the technical value. Think about the velocity, the speed where you can implement these solutions and moving in the right direction according to plan, and scalability. If you have 100 casting cells across your operation, think big, start small. Start with 2 or 3 key assets and think about how scalable that template is to the remainder of your organization. And think ROI. What is the business case? And in fact, a 1% scrap reduction in a mid-sized casting operation is near $250,000 per plant per year in annual savings. And this hard ROI does not include warranty mitigations or recall claim mitigations and other business cases that we'll talk about here in a second. So let's go back and define predictive quality for a second before going into the case studies. I like this definition. I like to actually read this definition because it makes a lot of sense. A predictive quality solution aims to really do 3 things. It detects deviations, it diagnoses quality issues, and it predicts potential deviations in your critical process parameters, right, which are usually your machine and ambient condition parameters, and how they impact the actual final product quality that you're producing on that machine. So we talked about cost of scrap, right? The power of 1%, a 1% or a fractional reduction in scrap or improvement in scrap is significant for the business. It's hard ROI. But there's also other things. There is lost profits. because you have to over-inspect parts, right? 100% inspections are costly to the business. They take time. And in many cases, it's not possible in very high volume operations. And then if this part actually leaves the casting machine and it goes to the next part of the cycle, which is machining, and then it might go to paint, it might go to assembly, and it might go to the customer, traceability issues may occur. Warranty claims may occur if the batch or the product is defective when it reaches the customer. And then the price to rework that part is becoming priceless. It's exponentially increasing as it's moving down the value stream. And then when it reaches the customer, it's safety critical and it's priceless to the business. So how can we mitigate quality issues at the source? How can we catch and predict and diagnose a defect right on the casting machine, for example, right on the first operation, right at the source, before it goes down the value stream or before it goes to the end user? That is the goal here of using industrial AI for predictive product quality. So there's a lot that goes into this. Unlike predictive maintenance, where you're looking up key parameters of the machine and maybe some add-on sensors, predictive quality is more thorough. It is more involved. You need information from multiple sources. You need not just your machine process parameters, but you may need material properties of the actual part that you're machining on the machine. We'll show you an example of that, actually, of bringing material properties of the steel coil that is actually used to make the part, because that's actually impacting the quality of the part. The product specification you're producing. There are thresholds, right, that your process parameters have to stay within when you're producing a part. So you have to maintain those thresholds while you're manufacturing. Inspection information from quality measurements that may have been done on the part, right, which may be kept in your quality system or SPC system. And of course, expert domain knowledge, right, because we know, or the experts know, the type of defects that typically occur on that type of product. So in order to achieve our business case here, we need to think and find what is the right data model here. And in many cases, a challenge is the data is not synchronized. There is no synchronization between the process parameters and between the product parameters. And such a lack of synchronization makes it difficult for industrial AI to be applied. So connectivity and having synchronized data between the process and the product is key to success, and we'll show that in the case studies. So where is predictive quality used? It is not just used in automotive high-pressure die casting. It's used also in the process industry, as an example. In the semiconductor industry, you're making chips, silicon chips on a fab, right? And it's critical to correlate actually hundreds, if not thousands, of chemical type of process parameters on a semiconductor fab to the end product, to the actual chip that is being produced, right? So it's truly a big data project in process manufacturing. You're dealing with high volumes of data. It's a data-rich type of scenario, and you're trying to find a way to identify issues with the actual part being produced before they occur in order to improve quality and to reduce rework and to reduce lost production time. So it is not just about casting machines in automotive. There are semiconductor electronic processes using this today, and of course heavily regulated manufacturing where safety and health is paramount, like food and beverage as an example. So very quickly, what do we need to make this happen? Okay, first we need to understand the type of events that may occur when quality issues occur, and you have drifts in process parameters on the machine that may lead to quality issues. Ambient or environmental conditions sometimes have an impact depending on the application. Sometimes machines may not be configured properly. Maybe the recipe or the NC program on the machine may not have the proper settings, or it might be a human-induced error that causes this to go down. And equipment degrading, actually, or potentially failing may also lead to quality issues on the part that is being produced. So to make this happen, we need inputs for the key signals or the process parameters, and that is application dependent. It will be different from a casting machine to a semiconductor fab to a CNC machine spindle that is making a part, right? So it's important to understand that data model, and it's important to correlate it with historic product quality data, keeping in mind that different types of scrap issues may occur on the machine. Scrap type A versus a porosity issue type B are different types of scrap modes, and they also may impact the models that are being produced. What is the output? So a predictive quality solution needs to obviously, and in a more real-time fashion, within the cycle time of the part, give a prediction. So is this green, yellow, red? It's predicted to be a good part. It's yellow, maybe it's a suspect part. I still should quarantine that part. Or it's red. With a high level of accuracy, we're predicting a defect on this part, and it should be segregated or quarantined. And in addition to this, it should provide the real-time intuitive information for the quality personnel and the shop floor personnel to use that data to make decisions, right? And it should have the ability to be configured, because there are different warnings and alarm thresholds that may occur on those process parameters, and we'll show some examples of that. So there is also the configurability and the interoperability of those solutions should be high, keeping in mind the volumes of data and how mission critical those solutions are to the business. So with this, I'm very pleased to invite back Dr. David Siegel. David will guide us through 3 case studies that are very relevant for predictive quality. David, thanks for being here today, and I'll hand it to you.
Thank you, Mo. Yeah, let's get into some of the examples and case studies focused on using AI to improve the quality. So we'll go through these predictive quality case studies. And the first case study is on process optimization for a CPG manufacturer. And if you look at this particular case study, we always start with the pain point. What is really the business case that is driving their motivation and initiative to improve their process and ultimately improve their product quality? And for them, they had increased warranty claims, issues with scrap. Those were the main motivating factors to consider for why they wanted to go on this digital journey and use the predictive analytics and artificial intelligence to improve their process and ultimately reduce scrap. So the main focus in this case was on scrap reduction and improving the process. And in terms of how we developed the solution, it was kind of a step-by-step approach. We looked at what data we would need, including not just the data from the machines, what maybe input settings or things upstream that maybe are affecting the quality. And with that, we configured the artificial intelligence and machine learning solution to understand the process relationship between the process parameters and quality. And once we modeled that relationship, we can then determine what adjustments are needed to make more likely better parts and have a lower chance of having scrap parts. So it's kind of a combined model of understanding the relationship between the process parameters and quality, and then running through an optimization routine to determine what offsets are the most important for determining what adjustments are needed. So with that in mind, let's get a little bit more into the particular case study. And in this case, we're looking at a discrete manufacturing application. In terms of the input data that we're looking at, it includes the steel coil as kind of the input data that is coming in. And within the steel coil, there are different material properties that also may affect the quality. And one of the main key process in this manufacturing line is the forming station. So we're collecting data from the stamping machine, maybe the pressure, the tonnage, and things of that nature. And we also want to relate those to the actual quality part at the end of this process, which is these finished ribs, and there's certain critical dimensions or whether they're cracked or not cracked that we're trying to correlate the data to. So if you view it from like a high-level perspective in terms of what are the inputs, what analysis is actually performed, and what are the outputs, this chart does a pretty good job of trying to summarize that. Again, the focus is on scrap reduction, and in terms of the input data that is coming in that we're using to learn this relationship between the inputs and in this case outputs or quality, we have the steel coil, which includes the material properties of the steel coil, different operating parameters and settings, as well as various sensor readings that are from the stamping equipment. And from there, we then want to look at what analysis can be done to understand this relationship and then determine what adjustments are needed. So first it's trying to model that relationship between all these input data and these outputs. Use the machine learning models to learn that input to output relationship. And once we know that, we can then determine if any adjustments are needed on the machine to improve the quality and reduce the risk of having scrap parts. And that's the general idea. So learning the relationship and then optimizing the settings to make the machine more likely to produce better quality parts and have a lower percentage of scrap. So in terms of how the user would interact with the software, so they would have kind of that main action dashboard that will tell them the health of their machine, the health of their process, and if any adjustment is needed on their process. And that's kind of the first level view. But in these kind of complementary views that you'll see in the next couple slides, the user may want to take a deeper dive to understand what are the root causes, what are those actual parameters that are maybe driving the quality issues. And here in this case, we're actually looking at one of the quality parameters, the rib height, and they can kind of zoom in and kind of visualize the dashboard. In this case, also see, for example, maybe this particular quality issue is related to more variation in these rib height parameters. So they can then, kind of narrow down and focus on that particular issue, because ultimately it goes down to what adjustment is needed in the process to ultimately improve the process and reduce the amount of scrap that is coming out for the process. And there's some additional views as well. For example, maybe you want to look at multiple parameters together and see if those combinations of parameters lead to a higher risk of scrap. So you can kind of visualize these information in the heat map in the software. In this case, you can kind of see that maybe in this example, when the temperature is a bit lower, you have maybe a higher probability of having scrap. So that may be an additional insight that you would use to then adjust what is needed in this particular process. Again, all focused on improving your quality and reducing the percentage of scrap. So to kind of take some takeaways or conclusions from this particular study and application, overall the solution was very successful in terms of detecting issues at precision of over 88%. So the model itself was very accurate, and there was a very clear return on investment for this particular solution once it was implemented, and it led to a few percentage reduction in scrap. And as Mo was alluding to, going back to the automotive example with the high pressure casting, even if a single percentage of reduction in scrap can provide hundreds of thousands of dollars savings, not just for the casting application that we'll get to a little bit later, but even for this CPG manufacturing use case as well. So the second application is focused on an automotive client that was also looking at quality improvement. We'll talk about our approach based on a machine learning model using anomaly detection, and we'll talk about some of the outcomes, what were the inputs, and how the solution was deployed and worked. So for this particular use case, we always again start with the business case, and for them they also had pain points of issues with inspection errors, not as much yield as they would like, so also scrap issues as well. And for them, it was not just a matter of reducing the scrap. They also wanted to diagnose the particular issue in the process, so they would not just address it as a kind of a one-time basis, but they could also maybe prevent the scrap issues from occurring later on. So the more you understand about your process, the more you can actually make it less likely to have these scrap issues in the future as well. So in this case, we're looking at early indication of the issue. It's focused on a casting application, a low-pressure casting application, and not just detection of the issue, understanding what factors are contributing to those anomalous process conditions which are leading to bad quality. So that is the focus for this particular study. This is a screenshot of the deployed solution. It's showing what we call the health of the part. In this case, they're making automotive components, and each dot represents one part. And the red or the yellow points are indications of the process being anomalous or unusual or not as expected. And in addition to indicating at an early point in the process, in this case right at the after it finishes the casting process, they can detect this issue very quickly. They would also know what variables are contributing to that particular issue, pressure parameter, or maybe a temperature setting, or maybe even it's related to a certain cycle time within the process taking longer or shorter than expected. That can also cause issues with the casting process, related to maybe defects in porosity or things of that nature. So that additional insight of diagnosis was very helpful, so they could then understand what was causing that issue and maybe prevent it from occurring later on as well. In addition to the last case study for the CPG manufacturer, it's important to provide that kind of high-level information about what is wrong with your process, what is the health of your process, what variables are contributing to that, but still, I would say, very important to have those complementary views so the user can then take a deeper dive as needed. For example, maybe they want to look at, the system was telling you that the furnace pressure was the main contributor. You can then take a deeper dive and compare that particular run for the furnace pressure to other previous, maybe normal runs where the quality was acceptable, and that will allow you to kind of confirm the analysis result and also take the appropriate action to adjust the process and ultimately prevent these scrap issues from occurring in the future. So there's some conclusions. I think overall the solution was also very successful. For this automotive client, we benchmarked with their manual inspections, and overall this was the solution was more robust than their manual inspections that they had for this particular process. It actually identified 96% of the defective parts, so it had a very good, robust detection of these defects, and we feel that the solution could be applied not just to this automotive customer, but also many other customers in other industries, whether it be automotive manufacturing, electronics manufacturing, aerospace, process industry. There are a lot of other applications that this solution could be applied to. So the last case study is also with an automotive client, and it's in this case focused on high pressure die casting, and we'll talk about a little bit more in detail about the business case and why this case study was so focused on early detection and how that impacts the return on investment and the value that they could get as the cost of the part and the scrap cost increases at each part of the manufacturing process. So yeah, the business case is always very important, and for this automotive customer, they had an aluminum casting operation. That was what they were doing at the particular factory, and their current status was they had 3.5% scrap, which is not. It's kind of probably close to what the typical average is in terms of an automotive facility. But of course they would want to reduce that. But when we looked at it more closely, when we talked to some of their engineers and managers, what we found is that it's not as much focused on scrap reduction, but on what part of the process you detect the issue. And the earlier you can detect the potential issue for scrap, that's where the big business savings is. So for example, the cost of a part is maybe around $4 at the foundry. And as you add additional steps to it, for example, machining, the cost of the part goes up to $11. And as you include assembly, it goes up to $28. And eventually, the cost increases more and more until it eventually is the finalized part that is provided to the customer. And if you look at it in terms of the cost of scrap, the cost of scrap is much lower when you catch it at the foundry. And as you add all these additional steps at machining, assembly, those costs go exponentially higher. So when you look at it, the main focus is that if you can catch the defects at a very early stage at the foundry, that's where you would get a really good business result and return on your investment. That's where the big value is in this case for this application. So yeah, you're looking at, as Mo mentioned, 1% reduction in scrap or detecting at these early stages. You're looking at hundreds of thousands of dollars savings per plant. So let's look at a little bit in terms of the actual equipment. So this is a picture of the die casting cell. So it includes not just the actual casting equipment itself, but also the auxiliary equipment, robotics for material handling, furnaces, and so on. And then if you look at the data collection, we're using various protocols like OPC, UA, and other methods to then determine what data is needed to understand the casting process. And we'll talk a little bit in this slide about what data we're actually collecting. So we're looking at, for example, in terms of pressure, the pressure of the accumulator, the ejector pressure as well, measurements of airflow, measurements of air pressure, as well as information related to temperature and other things as well. And in addition, we also were looking at not just these parameters as a single value, but also their curves or shapes. And that analysis, what we were doing is we were using machine learning on the data at the edge to then determine very quickly whether the part was in a healthy condition, or if there was a potential for this part to be out of spec and have a potential issue with scrap. So it's really, I'd say, artificial intelligence and machine learning applied on the edge, so we could have the fastest results, and we could send those results actually not to an operator, but in actuality to the actual robot that would then put the part in a good bin or a bad bin. So the whole system was automated. It was actually determining whether the parts were good or bad and sending them directly into that appropriate bin, as opposed to having a human intervention to then take the part out. So it's all fully automated predictive quality system. These are some screenshots of the system that was realized for this casting application. So as we were mentioning, the analytics are done on the edge, but we also have visualization that the user can see to kind of track trends and patterns over time, as well as dashboards that can give you a very good summary information of what the overall condition is of your casting process for your various cells, as well as a factory level view. And there's also additional reports and information, so the plant managers and other responsible personnel can kind of review the results in a more summary manner, and also the process engineers that need the more detailed view can take that deeper look as well. So with that in mind, I'll go to the next slide, where I'll pass the ball to Mo to go through the conclusions and remaining discussion for the webinar.
Thank you, David. Thank you very much for the 3 case studies that you presented. And I think these slides will actually be a good summary of the case studies, because at the end of the day, the case studies that Dr. Siegel went through is really a 3-part implementation process. The first part is, where's my data? I need synchronized data. I need data from the machine, data from quality, data from the process, and so on and so forth. So it's very important to get connected and make sure that data is available. Data quality is important. The integrity of the data is important. And then bringing that data through the industrial AI type of solutions and approaches that David went through, and then presenting the results intuitively to the end user, which could be a maintenance person as part of the predictive maintenance program, or it could be the quality person or the operator of that line, where we are focusing on the part health and the part defect prediction, right? Which was kind of the goal of this presentation today. And the 6-step process that is shown here is actually the process that was basically taken through the 3 case studies that were shown. And the first being data collection, next being processing the data, cleansing, removing outliers, synchronization, and all that, and then extracting meaningful features from the data, the indicators and the metrics from the raw data, and then using that to train either a supervised or an unsupervised model, depending on the application, okay? And I believe in the predictive quality world, it is more of a supervised learning scenario in most cases, because we would need labels of the different quality or scrap issues that are actually happening, right? And that is used to train the model. And then you'll be able to assess the part health, like the example David showed, green, yellow, red, good, suspect, bad, or defect. And then prediction, which is in this case a part prediction, okay, with an accuracy of sorts. And then a diagnostic, which is part diagnostics, and understanding, is this a porosity issue I'm predicting on my part, or is it a different type of defect? So supervised learning it could actually be key here in the predictive quality world. I think that was potentially one of the questions that was asked by the audience. Talking about templates, right? I mean, we talked about a CPG manufacturer with grinding machines. We talked about casting. We talked about high pressure casting, low pressure casting. But it is important to understand that there is a breadth and depth of applications out there in the manufacturing world. It is not a one-size-fits-all, but there are, templates and systematic approaches that manufacturers should follow in order to deploy these types of solutions. I'll give you an example. In the robotics world, for example, you're doing spot welding, or you're doing laser welding, or you're doing ultrasonic welding. There are quality issues there, right? The quality of the actual weld of the robot is a quality issue. So predictive quality could also be an application in the robotics domain, right? If you look at CNC machines, you have a spindle bearing with a tool, and if the tool chatters or unbalances, you might make a part that has a defect. The surface texture or the surface roughness of the part may be out of whack, right? So that's a quality issue. So there is also a play for predictive quality and zero defect applications in the CNC machine tool world, right? So we've selected 3 applications to show you today, but of course, if you have questions about any of the other applications, by all means, do contact us. Very quickly, how can you get started, right? So it's important to think big and to have a strategy and to have a multidisciplinary team in place. But it's also important to start small and to be very focused on the business case and the value from these types of solutions. And then to scale fast, right? To celebrate the success and learn the lessons learned and scale fast using a template-based approach. So it's a simple process that we recommend and we follow. 3D process, you discover what am I looking for, you design it, and you deliver it, right? And in the first step, there are assessments that need to be conducted. It's about technology, process, and people, right? The application of AI is not just about technology. There's process and there's people. So where's the team? Where's the plant? What's my maturity level? Do I have the right data? These are all assessment and discovery questions and potential training that may be required. This goes to a series of design workshops where those templates can be configured for the needs of the user. With regards to predictive quality, for example, I need to understand, do I have the right data collection? Do I need to add on hardware? What type of software may be required? What type of services and training are entailed to deploy these AI types of solutions? And of course, starting small to confirm some critical workplaces in a critical plant where you can actually initiate a case study, a use case, and have an ROI case documented for that. Then the solution, it can actually be deployed, all right, as a proof of value. A proof of value is an ROI business case backed by a technology that is implemented on a factory floor, providing value to the end user. And that leads to a lessons learned approach and potentially building a center of excellence team around it. So, digital talent within your environment, within your plant that is able to collaborate and kind of fill that gap between IT and OT, right? Information technology, operational technology, including data engineers, potentially data scientists, folks from the business side, domain experts when it comes to casting or other processes, and then have the internal momentum to be able to scale those solutions. So in summary, the Quality 4.0 initiative and predictive quality is actually not just about manufacturing, although we focus our efforts here today on that specific area of the value chain. But quality is of essence in the whole value stream, in the whole digital thread, from design to manufacturing to aftermarket, right? We focus today on the application of industrial AI in manufacturing, but by all means, Quality 4.0 and predictive quality has many other applications. Predictive quality really in manufacturing aims to detect, diagnose, and predict deviations and issues in the product quality that you're actually producing. And as David had also mentioned several times, it's important to catch the defect as early as possible in your value stream before it goes to the next process and before it ships to the customer, causing warranty or other recall claim issues. And we're happy to have shared with you 3 use cases today. The first one is from a CPG manufacturer, where you have seen how personnel can actually interact and adjust the process in order to maximize efficiency and optimize the line. You've looked at a low-pressure casting success story here with high prediction accuracy, low false alarm rates, where you're catching issues on a line that makes wheels, steel wheels, I believe, or aluminum wheels, very fast cycle times, and you need to catch that wheel before it goes on a truck, right? It's a safety critical piece of equipment that you're producing. And we looked at high pressure casting, where you're correlating big data, 40, 50 process parameters to quality of the actual aluminum cast being produced. And you need to make very quick and prescriptive, precise decisions on whether this is a good or a bad part, and you're auto-segregating the part right at the source before it leaves the casting machine and goes to the next process, right? So that's what we wanted to share with you today. Here's my contact information. Here's David's contact information. Connect with us on LinkedIn, shoot us an email, and Kevin, back to you. Happy to answer any questions that might be out there. Don't hear you, Kevin.
Sorry about that. Thanks, Mo, and thanks, David, for such thorough presentations. To our audience, you've sent us some questions already. Please send us some more. We'll now proceed to the Q&A session. David, Mo alluded to the data science, data engineering side of the case studies that you presented, but we'd like to hear it from you. How substantial was the data engineering exercise typically in these case studies, if there is a typical? And then in kind of a two-part question, what was the relationship between the data scientists and the subject matter experts when it came to the different processes involved, and how did that evolve over time, if I may ask?
David, you want to take a shot at the data engineering and the domain knowledge?
Yeah, maybe I'll address the second part first. So what we found from our experience is that the best data scientists usually have at least an undergraduate degree in engineering when they work in these manufacturing applications. That way they can at least speak the same language as we interact with the domain experts from the manufacturing side, whether they be from the maintenance side for predictive maintenance applications or for the process side for the predictive quality applications. But it really is I would say a marriage between the two of applying appropriate data science, but not applying it in a vacuum, and incorporating domain knowledge, whether it be in extracting patterns from the data, for maybe selecting which inputs you want to include in your model. Those are all important steps. And we found that by including a data scientist that has at least an engineering background is helpful, and also finding the right counterparts to work together to build that solution and deploy that solution for the manufacturing customer. For the second part, I think my understanding about data engineering, we call them more solution engineers. So they're the ones that help ultimately deploy these models. So they need to prepare the pipeline of data correctly, including the connectivity of putting in the data from the different sources, and ultimately configuring the software, deploying it, making sure everything is flowing smoothly. And that is always a part of the solution. Usually we have at least a data science team working on the project with the domain experts from the customer side, and also we have solution engineers working on making sure that the solution is deployed correctly and everything is flowing correctly. So both are used. Maybe I'll let Mo add any additional comments to that.
Yeah, I fully agree with you, David, on the domain knowledge. And my short comment on the data engineering or the solution engineering is, there is a challenge with predictive quality, which we alluded to in the presentation, in that we need synchronized data and we need supervised learning. We need historical information that relates process and quality. And in many cases, that infrastructure is not there. And sometimes that traceability of the parts is not there. And that, of course, hinders such predictive quality implementations. So I think it is important to do an assessment of where you are today and, quote unquote, the data maturity of your organization, so that we can put the right people performing the right tasks, including the solution engineers, domain experts, and the data scientists.
Well, thanks, Mo. Mo, another question for you. you mentioned that the majority or most of your experience is on the discrete manufacturing side. And that distinction between discrete and process is so basic to being human as is the question, how much or how many? So it just kind of goes right through almost everything that engineers work on in those industries. But my question to you is, how do you distinguish in terms of what we're talking about here, predictive quality? What are the differences between discrete and process as you view them?
I'll give it a short start. I mean, we have done discrete applications like you're making an aluminum cast on a high-pressure die-cast cell. We've done semiconductor applications where you have, a chemical process making semiconductor, silicon chips. So we've done discrete, we've done process. I think the maturity of the data, the availability of the data richness, thousands of parameters in semiconductor versus 50 parameters in casting. I mean, I think there are some key differentiators there. David, how do you feel between discrete versus process, if you want to add to that?
I would say discrete manufacturing is a little bit more new, this area of predictive quality. And I agree with Mo that the volume of data, the connectivity is probably a little bit stronger, to be honest, in the process manufacturing side. We have worked, as Mo mentioned, with semiconductor manufacturing, as well as, for example, glass manufacturing, various processes. And they usually have, I'd say, a pretty good historian and SCADA system already in place. And for discrete manufacturing, that may not be readily available, so there is a little bit more work on the connectivity side. However, once you get past those, initial, efforts that are needed to get the connectivity in place, the underlying technology, I'd say, is very similar. You still have to, again, focus on the business case and the business needs, but a lot of the technology, I'd say, is very similar. Good.
Thanks, David. David, in the examples that you provided us, was supervised learning used or unsupervised learning used to define the parameters that affect quality?
Yeah, that's an excellent question. It's actually, we use both. It depends on the case study. For the CPG manufacturing example, the first case study, it was based on supervised models. It was just based on the number of defects that we had. There was sufficient data to try to learn that relationship. And also, since we were focusing on adjusting the process, the supervised model made more sense. And in the second example, the low-pressure casting for the wheel example, it was focused on anomaly detection, which in this case we're using unsupervised models. And also for the high-pressure casting, it was also focused on more pattern recognition and unsupervised model anomaly detection. And I would say both can be used, and actually both, you could also calculate what variables are contributing to both models, both unsupervised and supervised models. So they're both, I would say, valid approaches to consider for this application.
Thanks, David. Another question from our listeners. Have you also expanded the predictive quality solution back to potential design flaws? David, I would ask you to answer that question.
Yeah. David, maybe some feedback on what we've done around predictive analytics in the design process?
Yeah, so I'd say there's some initial work there, but I think there's a long way to go in terms of really, I'd say, closing the loop in terms of understanding these process defects and maybe understanding whether it has to do with, maybe the design itself in the sense that maybe it wasn't designed for manufacturing appropriately, or there's, certain issues that are maybe making it more challenging to manufacture the part with a good quality. Now, we have also linked the quality and predictive quality information to even further downstream, so kind of the reverse. Instead of going back to design, actually looking at it in terms of what leads to actually warranty claims and things like that. So you actually can go both directions. I would say it's more at the early stages. It's it's already challenging to get the predictive quality solution relating the process to the quality inspection results. But to go back to design, I think is an additional step, which we're working on, as well as to go a step forward and look at how it impacts warranty claims as well is also very interesting. We've done a little bit of work in that area. Mo, is there anything else you want to kind of add to that?
No, I think that's a great, actually, feedback to design. And I think we've had clients that want to marry multiple areas of kind of the digital thread. So taking data from manufacturing or taking data from the aftermarket field and using that to go back to the manufacturing design to create future better generations of new products. So there surely is a role of industrial AI and predictive quality in those applications, as David said.
Well, thanks, Mo. Mo, which is easier to do, predictive maintenance or predictive quality? Or is that a meaningless comparison?
We really think is just what is the business case, what are you trying to achieve, what's your technology, process, and people to make this happen, and you will be as good as your weakest link, I would say. If your weakest link is talent, you have to fix that up. If your weakest link is technology and infrastructure, you got to take ways to fix that up. I think you can be very successful with either or if you have the right combination of technology, process, and people, and the right business case and backing to make it happen.
David, any further comment on that one?
No, I think, yeah, both are, I would say, we've demonstrated, very successful solutions and deployments for both. I would say that one nice attribute of predictive quality is to kind of differentiate is that predictive maintenance, it may take a little bit longer to get that initial return on investment because failures don't happen, for example, every day, but you can start seeing improvements in scrap, even on daily and weekly basis. So the predictive quality may see earlier returns than the predictive maintenance. But in terms of the solution deployment, I think as long as you do things properly and you have the right data and you understand the business case and the right objectives, I think both are very feasible currently.
Good. We're about out of time for our webinar today, so what I'd like to do is ask a final question of David, and I'm just interested as to whether you think there is such a thing as artificial intelligence and whether it's going to be used more in applications like the one you described.
Yeah, I'll take a first stab at this. So I think I would say that artificial intelligence is an evolving field. I think machine learning technically is considered under that umbrella. So to a certain degree, it has been used. But in terms of, I would say, the more science fiction or the more, I'd say, research development stages in terms of, the actual ability to kind of learn as it goes and, actually the ability to reason, that's still at the very early stages. So these are more, I'd say, using machine learning types of models, unsupervised and supervised is kind of the current state, whether they be different types of, deep learning or shallow networks or other types of machine learning models, unsupervised models. That's kind of the current state. I think the idea of using AI to actually reason like a human is still a ways to go. That's my perspective. Maybe Mo, if you want to also, comment.
I fully agree, David. It's really an enabling tool. It's an umbrella of mathematical techniques, including machine learning and deep learning. We talked a lot today about connected assets and connected products regarding quality, but also we talked about humans, right? So the role of connected workers and the AI not being here to replace them, but to actually be a tool that supports them. So use of augmented reality and unique approaches applying AI to actually support humans to do their job better and run machines better and make better parts. I think that's also part of the equation. And hey, maybe a future webinar, Kevin, as a part 3 to this.
I was taking notes while you were speaking, so it's right around the corner. Thanks, Mo. And I really want to thank our audience for the great questions today and our speakers for sharing their time and expertise. I really appreciate it. I'd also like to extend special thanks to our sponsors, Avnet, Epicor, and Oracle NetSuite for sponsoring today's event. Now that we're just about done, we'd like to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webcasts. Finally, on behalf of Plant Engineering, I'd like to thank you for attending. That concludes our webcast. Thanks, and we'll see you next time.